Okay, so the last speaker of today is Max Pinheiro Jr. From University of Toronto, was that? But I think, yeah, no, that was the other speaker. Sorry, so it's Marseille University. So Max, go ahead.
Thank you. First of all, thank you very much for the organizers to give me this opportunity to present my work. And you have already seen many examples in the previous talks about learning. And here I will try to go a bit deeper on this analysis. And I will talk about one project that I have started more or less 1.5 years ago to develop a program dedicated to the this kind of unsupervised learning analysis for molecular dynamics, and in particular for excited states molecular dynamics. So okay, it goes too fast, maybe. Let me just come back. Okay, so to understand, I need to move this. I don't know how to move that thing. Someone knows how to do it. Maybe. I'm trying to move like this.
That done? No.
Ah, okay, it works. Okay, perfect. Yeah,
this way?
Yes, better. Much
Sorry.
better.
Yeah.
Oh, thank you very much. Oh, okay. Yeah, so to understand why do we need something so special to analyze this kind of data, we should see molecular very efficient and effective data generate. What I mean by that is that during some molecular dynamic simulations, some ab initio, for instance, molecular dynamic simulation, what we have is a sequence of graph-like objects, which are the frames of the dynamics, with some configuration of the molecule that we can convert into some sort of numerical descriptors. And then for every time step of the dynamics, we just stack all those vectors that is shown in this table over here. And we can even augment this table with some other quantum properties that is available in our data set. So the task is, given some table big like this one, we want to figure out what are the important internal coordinates of the molecule that is responsible for some sort of chemical reaction or chemical process in general that is more important in this process. In particular, if we are talking about surface hopping dynamics, as was already introduced in the previous talk, we need to add one more component to this diagram, that is the number of trajectories or multiple trajectories that we should execute to get the quantum information from the statistical ensemble of this set of trajectories. That we have a big data problem that will increase as your system increase, and also when we go to a long time scale. And then in this bunch of data, we want to extract some chemical insights. And if your molecule is too complicated, the normal techniques like mapping some key angles in the molecule maybe not the good way to go. And we are trying to develop some set of tools to be able to describe this problem. And just a quick recap of we have already seen previously. The type of dynamics that we are interested in is the excited state dynamics, meaning that dynamic from some excited state surface, and we let the system to evolve using, in our case, classical equation functions to describe this path in white here, and let the system evolve until it reach some region of a small energy gap, which is more likely to have a jump from one surface to the other, and then the system can continue and probably have some sort of transformation on this region. And then we have many possibilities to go from one surface to the other. You may jump at some point, but you can still continue in the same surface. And again, our problem here is to understand what is the characteristic of the molecule along each one of these paths, or extract some of the important coordinates of the molecule along this trajectory. So about a bit more detailed explanation in the talk Wednesday by Professor Mario Bavati, which is my supervisor in this project. And in our group, we developed the NewtonX program to do this kind of a simulation. So then, unsupervised learning, in fact, is not something new for the community of molecular dynamics. If you look at the literature, you can see that in the past 10 years or so, we have seen an increasing interest on this field, and with more and more publications dedicated to the analysis of molecular dynamics using these techniques. And as a result of this scientific interest, we can also see some softwares that try to address this kind of problems, especially in the case of biomolecules or eventually only classical molecular dynamics, which bring us to some problems that we are able to identify. That most of these papers and also the programs focus on the they are interested to address specific problems that only need very few unsupervised learning methods. In our case, we found that these kind of techniques are not really suitable for this type of non-adiabatic dynamics. And think on these problems, we are trying to contribute to bridging this gap between the unsupervised learning analysis and trajectory surface hopping, introducing a new program, Python program, to take care of this analysis, mostly focused again on the excited states. And we are also trying to provide a more diverse set of techniques to use in this type of analysis, and make the program more suitable for this type of dynamics. So at the end of the day, what we do is to have some more complete and general integrated framework, where this unsupervised learning analysis can either be used to as a post-processing tool only for the analysis of the data that comes from the dynamics, or we can even use these techniques to improve the quality of our training set. For example, by removing some collinearity between features, that is also possible to do with these kind of techniques, or having a more smart way of sampling the data points to generate our training set. And all of this is now being connected to a single framework involving the ML Atom program developed by Professor Pavlo Drau in China, which I'm also collaborating, and with the program that is the main program responsible to run the dynamics, either with the supervised learning and also connected now with UlaMDyn to do this analysis. So how the program works. So we try to develop a program that can attend a more diverse set of users. So we have a Python API that can be easily accessed to design your own scripts, or we can either use these analysis tools via command line interface. And we create different modules to deal with this whole pipeline of the data analysis that starts, of course, with a collection of data. Then we need to convert this into some descriptors. You have already seen some examples of descriptor before. We have some other types of programs dedicated to specific analysis, like the kinetic energy of the system, for the statistics also. And finally, what is the topic for today, that is the unsupervised learning part. And in this case, the program was built on top of some well-known package, Python data science community, like scikit-learn, for instance, for the modeling part, and the pandas for the data analysis. So the first step in this pipeline is to collect our data. So NewtonX will generate for us many independent trajectories. In each one of these folders, we have some sort of text files, and we need to extract the number from this text file to build the matrix that I shown in the first slide. So we this was actually some very time-consuming part, because to select these numbers from the text file sometimes can be a bit tricky. But then we have something that looks like this table, which contain in each row information of a given frame of our trajectory. So I think this is already a thing in the program, because it facilitates to share with the others. So we have all these data all these data sets in a CSV format that can be easily opened and analyzed by many different programs. So that's the starting point for the analysis, is to build this set of data. And then we come to the part of the unsupervised learning itself. So you've already seen some definition for that. So in the case of supervised learning, we have target function available to penalize our algorithm when it takes a wrong decision. In the case of unsupervised learning, we don't have this. When I say that we don't have this, I found this many times even in textbooks. Does it mean that your data set cannot contain any information of labels? It can contain information of labels. The difference is that the cost function itself depends only of your inputs. And in fact, you can even use labels, if it's available, to some sort of check if your clustering approach or dimensionality reduction approach makes sense or not. So then, even if you have labels in your data set, it will not be used by construction of the model. So this is the fact that you does not depend of the labels is nice, because you don't need to compute thousands of single point calculations, for instance. But at the same time, it becomes much more difficult to analyze if your clustering approach is or not. So just to briefly mention, when we have a set of data points, here I'm showing some very simple example in two dimensions. We may be interested, for instance, to discover a set of points that share some similarity between them. And then we can attach to this group of points some label to say, these guys are similar and these guys are not. But you can see that here I could eventually merge these two groups together. And depending on the application, this could make more sense or not. And that's why I say that evaluating the performance of the model can be very difficult and tricky, because you can end up with different solutions for your problem just by changing your descriptor or just by changing your algorithm. So that makes unsupervised learning analysis quite challenging. But at the same time, when you let the program find figure out the pattern by itself, you are not introduced, or at least that's the main goal, some kind of human bias, because you are not assuming that a given coordinate of the molecule is the most. You let the program give you this information. So that's the main goal. And in unsupervised learning analysis, we have many different subdivisions, let's say, and one of them is the clustering analysis. And before in this picture, you can just give a label for those molecules that are similar to each other, and in this category, you can find many different types of program. You can also have data compression or projection of your data to a lower dimension, where you try to preserve as much as possible the information that you have in your original data space. And that's also quite nice, as you will see in a moment, because the simple scatter plot, you can eventually get some or chemical intuition about what you have obtained in the dynamics. So in the case of unsupervised learning, we can see the molecular dynamics data in two different ways. You can either consider each individual point of the many trajectories of every time step as a data point and compare these data points. So you need to define some metric of distance to compare pairs of data point, and every data point in this approach that I'm calling here the geometry space is a geometric state of the molecule during the dynamics. And here the idea is to find some similar set of geometries that may be related to a given chemical process in the system. You can either relate this afterwards with the time step of the simulation or some other external quantity that is available. The other one that I will briefly speak here, but it's not the topic for today, is the trajectory space, which means that when you run a dynamic simulation, you get time series object that is high dimensional, because each point is a vector describing the state of your molecule. And eventually you want to compare these signals between them, and they identify what is the different branches of the dynamics that your system can reach. Eventually you have a system that can break and form two different products, and you have a fraction of them just doesn't go for don't go through this path and generate different products. So the idea here is very challenging, but we have also already implemented one option of clustering this. Briefly mention the next step in our pipeline. Remember that we first collected all our data. This data set is mainly composed of XYZ coordinates. But we have seen already many examples that this kind of coordinates not good for machine learning model in general, not only for supervised learning, but if you want to do unsupervised learning, you also need some more specialized type of descriptor. So we have implemented some simple descriptors in our program to convert the XYZ geometry into something that can be learnable. One of them is this, it's called R2 type of descriptors. So you can derive some other set of descriptors from this. It's just to compute the pairwise distance between atoms and flatten these into a vector. That's one type of descriptor that we can use. And another one is very popular in the quantum chemistry community, is the Z matrix, which contains direct information of bonding angles and diagonals. So you already know very well. The advantage, why we choose something that is so simple. So if you go to the literature, you see SOAP descriptor, some other local descriptors. Why we choose something simple? Because at the end of the analysis, it's important to know which coordinate is playing a more important role during the dynamics. So we want to go back and understand what our clustering analysis or dimensionality reduction analysis is giving to us. So then if you have something that is directly connected with the molecular geometry, it's much easier to get this information. So in this first part, I will just mention about some examples about dimensionality reduction. Currently in our program, we have one linear model that is the principal component analysis, so very simple. And then we have the kernel extension of this model, the isometric feature mapping, which is, it's actually a manifold learning technique where the goal is to figure out the shape of your data. So here we have something that is intrinsically 2 dimensions, if you stretch this S into a plane, but is embedded in a 3-dimensional space. So when you use this kind of techniques, you are able to unfold this nonlinear shape into a plane like this in such a way that points that are far apart in the original dimension, you will still be found separated in this low dimensional representation. So I will give you some of the examples in the next slide of what this type of analysis can do. And the system that we have selected for that is the Fulvene molecule. So this is a very simple molecule where the system is high dimensional. Again, if you compute all the pairwise distance and put it to a value, you will see that this is a high dimensional object. But in practice, we have only 2 important main coordinates that dominate the dynamics of the system. The rotation of the CH2 group and the bond stretching between these 2 carbons here. So in the 2 cases, you can start from some point in the excited state and reach the intersection between the surface, or via this stretching, or sometimes combining this stretch and also the rotation. So the goal is to try to identify these coordinates from some low dimensional representation, for instance. And then we can do PCA analysis, where the color of the points is just the energy gap between the 2 states, the first state and the ground state. And we see that aside from these blue points that are far apart in the diagram, the others are kind of mixed with this energy gap. So this is not very insightful for us. But if you use the isomet, we can have a nice separation in this kind of ring topology of the data when projecting 2 dimensions, where these points here correspond to large energy gaps, and you have some dispersion of points here. If you look at these star markers that correspond to the Hopin geometries, they are also located as expected in the region of. Then we can kind of select a bunch of points and take a look at the distribution of the geometry in this case, because I already know beforehand that the bond length from the CH2 group to the ring is an important coordinate. I took a look at this distribution, and we can see that in fact the projection can separate these 2 types of geometry. So the geometries with the low energy gap are very different from the other with the high energy gap, mainly with respect to this bond stretching. This is just, we select, of course, a simple system to confirm is working well. We can extract some good analysis from this. But of course, for some more challenging system, maybe a few more comparisons with other coordinates. And then we can go to the clustering methods, where we have where the idea here is to take the data points in its original space. We don't necessarily need to do any projection in this case, and then try to find the set of geometries that correspond to some specific part of the potential energy surface, let's say. And, we have many different approaches. Here I'm showing only 3 of them that are available. And I will give you an example of this partitional method k-means. That is one of the most used and also simple method to implement. And the idea of k-means is to partition these groups using some linear boundaries that is called Voronoi cells. And we call this a hard partition scheme because every data point belongs to only one cluster. So it will divide in this way. So if your data set has some nonlinear shape, you may need to move to something like spectral clustering approach that is, well, it can be considered as a kernel version of k-means that is able to take this complicated of the data. So then, okay, in our case, what we do is to select some 15,000 random geometries from these 200 trajectories, and then we can do our clustering analysis using the pairwise distance descriptor. I selected here just as an example, meaning that I am assuming that my data set has 3 different clusters, and this is based on the previous analysis that we saw the blue, the green, and the red points more or less well split in the dimensional reduction analysis. But in practice, you should search for a good number of clusters in your data set. Okay, so then when we do this decomposition here, what we see is that again, for this bond stretching of the C5C6 bond length, we have most of the hopping geometries selected here, which means that probably this is the coordinate that is responsible for the jumping from the excited state surface to the ground state. And we can also do the histogram of the energy gap, even if it's not used in the data set as an input for the model. And we see that the cluster 2 contains most of the geometries that correspond to small energy gaps. So far, so good. It seems that it's working fine, but when you look at each one of these clusters, we can see that the algorithm has some difficulty to find the geometries that correspond to 90 degrees rotation of the group. So it's kind of mixed a lot of different angles here, and here it's missing the 90 degrees rotation. So it seems that the algorithm is not able to capture very well this rotation. But then what happens if we change our descriptor? So now we are working with the one version of the Z matrix, which is just the difference between the Z matrix of your frame and the Z matrix of some state geometry. And on top of this, we calculate sigmoid function just to have something that is normal between 0 and 1, some nonlinear distribution of these features. So for every coordinate, bond, angle, and dihedral, we apply this nonlinear transformation. When we do that and apply k-means again, now with a different descriptor, what we see is that the red cluster now contains most of the geometries that correspond to 90 degrees rotation, while the other 2 are differing one from the other, mostly with respect to the bond length, but not with respect to these rotations. So with this, we can get a much better description of our the point distribution. We see this red cluster here separated from the others. And again, if we look at the distribution of the energy gap, we see that we have two different types of energy gaps. So we have this yellow one that correspond to the bond stretching and leads result in geometry with this small energy gap. But as I said at the beginning, the rotation drives the system to this region energy gap, which is also captured in the cluster right here, because the two are kind of. So then, but let's suppose that we have some system that I don't know what are the coordinates. So I don't know that there is bond stretching or rotation or something that is playing an important role during the dynamics. How can we get some insights, or at least reduce the number of features that we should analyze to get this information? One possibility is to use combine, and that's also quite interesting in my opinion, combine the supervised learning after doing unsupervised learning. How we can do that? Well, once you do the clustering analysis, you have a column with the set of labels that the clustering analysis will give to it. And then you can apply some tree-based model, like random forest, for instance, to predict these cluster labels. It's a simple classifier. And the reason for that is because the way tree-based model will partition your data space is very similar to what we do with k-means. But in this case, your cost function is looking to reproduce the cluster labels that you get from the k-means partition. So after doing that, what we can apply is a technique called permutation feature importance, where we select a column of our data set and then we show that column, and we see how the accuracy of this tree-based model decreases when we do the shuffle. If that particular feature is too sensitive to this change in the data set, we will assign a higher score in this diagram. Then we can rank our features, that is in this case based on the Z matrix. So then we have R is the bond length, here is the dihedral angle, and here is a normal angle between three atoms. So then we can construct this kind of rank of our features, where we see that the first one, which is this R6, R65 here, correspond to the bond structure. So it's matching very well with our previous analysis. And also for the rotation, that is much more difficult to describe in the clustering approach, because we have the number of points in this cluster is much smaller than we have for the others. But still, it appears as the fourth most important feature of our data set using this approach. So if we cut our diagram like more or less like here, we have a set of internal coordinates of the molecule that we can analyze. So we have seen the literature some other applications of the same type of approach, like using isomap for identifying different reaction paths. And if we go to some molecules that are much more flexible and have many degrees of freedom, it becomes quite complicated to do this analysis by hand in such a way that if you introduce these unsupervised learning techniques, you can get some very nice description of this reaction path. And we are also trying to go into this direction. And in our case, we have selected this PSP molecule that can rotate along many different axes. And in this paper of 2009, the task was exactly to identify all the types of rotation in the dynamics, but using some predefined rules. So let's say that one of these guys rotate by more than 30 degrees, then you just go there and say, okay, these guys belong to the OBF clusters. So you do this manually. And our goal now is to take a new data set that we have already constructed for this molecule, and try to figure out that if we are able to get similar numbers, similar description with a much less computational effort in a single chart using either dimensionality reduction or clustering analysis. And just to give you an example, if you use a principal component analysis for the data set, we can see 3 different branches for the ND of the dynamics. So some of the molecules end in different geometries. And we have also this set of ready points here that corresponds to a different cluster. So in total, we would have like 4 different types of geometries in the end of the trajectory. And now what we are looking for in the next steps, this is an ongoing project that I'm still working on, is to relate the characteristics of these ready cluster here with the different geometries that we in this paper. So this is something that I'm still working on. And with that, I would like just to give you some final message, some takeaway message. So we have seen that if you want to group your data in a meaningful way, it's important to analyze which type of descriptor you should consider. We have seen an example in which the R2 descriptor doesn't work, but if you change for of this Z matrix difference, you can get something much more reasonable. And in the case of clustering analysis, especially how you compute the distance between data points is very important. So in general, it's important to test different distance metrics. I have shown one example with the isometric feature mapping for dimensionality reduction, where we have used cost Euclidean distance, for instance. We have also to do some pre-processing steps, like data standardization is also important and should be considered carefully. In general, a good recommendation is also not rely on a single analysis like PCA, but instead should compare different algorithms to see if they one of them can give you some representation of your data in the low dimensional space. Something that I didn't have time to talk about is some algorithms in dimension reduction, what we call the reconstruction. And also, even if you don't have labels, you can compute some kind of score metrics to analyze how this is projection. So when you go from any dimensions to 2 dimensions to do like a scatter plot, you can calculate how much information you lose when you do this projection. So this is also important because you give you information of how reliable is your projection. And the same thing for the clustering approach. We have internal metrics that basically depends on how compact or the cohesivity of your cluster and how separated we are, because this is the most important concept in clustering. But also, you may want to analyze how your clustering is correlated to some other external feature of the data set. For example, the energy gap between 2 states. If you want to use some metric like this, you can a given cluster is let's say pure or have a high purity with respect to some external property that was not used for the clustering approach. In the last week, I give a tutorial about unsupervised learning that is available in GitHub. If some more about these techniques, there is a Jupyter notebook with some examples of coding how to do this analysis. And with that, I would like to thank you and also my group in Marseille and the funding agencies that is supporting our project.
Thank you, Max, for this very interesting contribution. Questions?
Yeah, I've got a question related to your Z matrix coordinates. So, for example, in Fulvene, you have a cycle, and Z matrix it's known to have some difficulty to represent the cycle. So, are you one bond which is present? So, is it a problem or not?
Yes, it can be a problem. For in the case of Fulvene, I think not a problem, but in fact there are some systems where you start with a planar ring structure and it can deform out of plane, and this motion out of plane can be difficult, as you said, to describe using Z matrix because it may involve more than only 4 atoms to describe that. Thinking on this problem, we have added some options to our program that the user can define some additional variables to augment these descriptors. So you can define a set of atoms up to, I think, 6 atoms, because in this case you can compare at least 2 rings. If this is the case, if you have some system that have 2 rings, but in principle you can take some 4 atoms that are not directly bonded to add more information about this out of plane motion. This is one possibility that is already available. Another one that we are trying to implement yet is the Pulai internal coordinates.
That's my next question. Okay.
In this this should take some time because it's not very easy to do, but we have some ideas to go in this direction.
So you want to go in the redundant coordinates?
Yes.
Okay. Yeah, that's true. To do.
More question about K-means analysis.
Okay.
How do you, why you choose to be, and why 2 are superposed? So
yeah, that's a question actually, because I passed it really fast in this part. Okay, so let me just go back to this diagram. So why I tried first, just to be clear, just for demonstration first, but I would not recommend you to simply say KA3 and be satisfied with that, because in general you have some metrics in clustering approach that I didn't discuss here, where you can evaluate what is the ideal number of clusters for your data. So it depends, for instance, of some metrics that you can calculate. But here you see that there is this big set of points blue, something that is kind of green to yellow here, and these red clusters. So it's not a very well-defined partition, I would say, because you have some overlap here and there, but at least you can identify by the colors with respect to this energy gap information that you KA3 seems to be a good guess. I would start with this because of this distribution of the colors, and then that's the way of playing with unsupervised. Normally, you have to work with both things. You project your data, you gain some insight about this to understand how the data is distributed, and then you can move, if it's the case, to some clustering approach. And I used KA3 for demonstration again, but it was this choice was based on this diagram that give me some idea that KA3 would be some good guess.
and then later in the histograms, can you show the in the histograms you showed after? I think
This one?
Yes, this one.
Because what
Cluster 1 and 3 are. superposed. So
yeah,
how can you
this
recognize?
superposition that you see here may happen because this information was not used for clustering.
Okay.
So the clustering approach doesn't know anything about the energy gap. I'm just looking at afterwards. I'm just looking at the clustering to see if I was able to get some meaningful distinction of my data set. So at least the ones that correspond to a small energy gap, a bunch of them are very well separated. So you have this peak here. But as I showed before, when I change the representation, I can get two different types of geometry with small energy gap. I can get geometry where we have the bone stretching that leads to a small energy gap, and I can have the rotated geometry that is also geometry with small energy gap. That's the reason why in the other picture we have these two clusters superposed.
Okay.
So the geometries are different between them because the red ones correspond to this and the yellow one correspond to this. But even in this case, you can distinguish what is the motion. So the rotation and the bond stretch, both cases leads to closing the gap.
Okay, thank you.
Any other question?
Yeah, I guess it follows. If I understand correctly, you do this dimension reduction. So then you can figure out how many clusters you want, and then you do this clustering analysis. But it seems that if after doing all this, if you don't really know what you want to look at, you're still lost, right? Because either you do this random forest and so on. But if you do this dimension reduction and you analyze those axes X1 and X2, it should give you those information that you are. So I don't get why you need all this prior knowledge, or if you need to this random forest.
Okay, good question. Let me just go back here. So yeah, for instance, in the case of the principal component analysis that is linear, we can express each component as a linear combination of your features. So then it's really straightforward to know which feature is contributing for this diagram, right? So you can see, let's say this is the PC1. We can check which one of the coordinates is responsible for the point spread along this direction. But this is not true if you go to some nonlinear dimensionality reduction like isomap. You cannot do this interpretation directly because you lose, because of this nonlinear transformation, it's not directed to get this information. So it's not true that X1 is a simple linear combination of your features. So I cannot say what is happening along this axis because of these nonlinear. This is true for basically these three different methods. Only linear PCA can give you this information directly, but sometimes it doesn't work very well. So you need to do something else.
I don't know this isomap, but I thought in Tisney you could still get some information on the axis with Tisney, but maybe I'm wrong.
Not really, because TSNE is actually based on some, as the name says, is some stochastic neighbor embedding. And even there is a problem that if you repeat TSNE multiple times, you can end up with different clustering structure because it's not a deterministic approach. In general, you can converge to some, well, the algorithm is very well done. So you can converge to some local minimum, but there is a possibility that if you run it again, you end up with different clustering structures. It's based on probabilistic theory. You just compare the probability of having neighbors to a given data point in low dimensional space, and you want that this probability is the same as in your high dimensional space. So you want to preserve this distribution around a given data point. That's what, well, roughly speaking, is more or less what TSNE does.
Okay, thanks.
Welcome.
Any other questions? Do we maybe have some question from the online audience? I don't know how to check this.
Check. I don't see question. Yeah.
Is there anything in chat?
I don't see anything in the chat. So, okay.
Nice echo. Okay, I would maybe still ask one more question.
Okay.
So on slide where you explain your choice of descriptors, so the distances, the symmetrices. So you said you made this choice, if I understood correctly, in favor of intuitive understanding or interpretation.
Mm-hmm. Mm-hmm.
Basically, if you think of descriptors as internal coordinates, you can transform from one side coordinates to other. I mean, like full set of the soaps, for instance, you can easily transform them back to Cartesians and from Cartesians to any other set of coordinates, right? So in principle, you can get the same kind of intuitive understanding when using any set of descriptors, right?
Yeah, to be sincere, I'm not very familiar with this connection between how to convert from one to the other. But as a first step, we decided to go for the simplest one. But in some cases, that there is room for improvement, of course, and it would be good to consider this more advanced, let's say, ways of representing. But it's just as you said, just introduce another step that is doing this. To add some more different types of descriptor. One of them, like I said, you can go back to XYZ, but typical way of going back. I think you have to do some.
So you do this numerically, iteratively, right?
Yeah,
but in principle, exactly. In principle.
Good to know. I need to investigate a bit more about this, but yeah, it's one of the directions I'm planning to do is to add more.
Okay, good, thank you. Okay, so since there are no more questions here, so I think and yeah, this was the last talk today. So I think we see each other tomorrow in the morning, 8:45. Okay. Yeah, that's not for online.